Hello everyone, and today we are going to discuss section 15.3. Section 15.3 deals with, I hope you and your family are doing safe first of all, and 15.3 deals with double integrals in polar coordinates. Okay, let me adjust my page so that I don't get so that I feel comfortable first. Yeah. So first of all, the section 15.2 was, I think it was double integrals in, if I understand it correctly, it was in double integrals in general regions. Okay, in general regions. So what we did in that section was we found the volume, we found the area. So when we found the volume, we did something like, you had a curve f of xy on the domain, and we found dx dy. Or using Fubini's theorem, we changed the order of integration, and we got this to be f of xy and dy dx over the entire region D, right? Now, why are we studying double integrals in polar coordinates? The reason being, sometimes evaluating double integrals in using rectangular coordinates will become difficult. Okay, you can refer to some problems in the textbook and you will see that. Okay. So we need an alternate route. We need an alternate route. Alternate path or route or alternate means to find the volume. So we are exploring. So we use double integrals using polar coordinates. This is you don't need much of an introduction to polar coordinates because you have seen them in Calc 1 or 2, I think. Okay, so what we really do is we replace to go from, you want to move from rectangular to polar coordinates. So what you do is you want to say x is r cosine theta, y is r sine theta. So you get x squared plus y squared is going to be, you're going to say r cosine theta squared plus r sine theta squared. Okay, so that's going to be r squared cosine squared theta plus r squared sine squared theta. Okay, and then that's going to give you what, r squared here, right? That's what it is, because you know that cosine squared theta plus sine squared theta equals 1, and that gives you r squared. The next thing is, of course, you have dA, and that is going to be dx dy, and you want to change it to some form of, in the form of d theta, r dr d theta. Okay, the answer is r dr d theta. Okay, but you might ask me, why do you want to do that? First of all, one is by the power invested in me, just accept from me. Okay, that's one. The other route is, we are gonna study something like change of coordinates of Jacobian in section, somewhere in section some section of chapter 15. Because of that, you will be able to see. The other is, there is a geometric interpretation. If you have a sector like this and you want to call this as r, and this is going to be d theta, so this is going to be d theta, so this length is going to be r d theta, right? R d theta. That's going to be because the arc is going to be the radius times the angle subtended at the center. Let's say if you extend this, okay, and let's say you extend this, and you get that. So you want to find what is, okay, this is dr d theta and this is dr. Let's say that you extend it a little bit and you want to find the dA there. The change in area. The change in area means that we are going to use a rectangle or a square approximation. So that's going to be length times the width. here the length is going to be dr and the width is going to be, or the width is going to be dr and the length is going to be r d theta. So that's going to be dA is going to be r dr d theta. So that's one way to understand. That means dA is nothing but dx dy. So you want to change dx dy to r dr d theta. Okay. The other way is, I mean, you know, if you are going to consider dx dy, it's going to be using the determinant is going to be dx dr. I hope I get it right. Okay. I don't know if I get it right or not. I'm going to try it. Okay. Dx d theta and dy dr and dy d theta, determinant of that. I mean, I will show you as to why this will become like that. Okay. So r dr d theta. So later on, not now. Okay. So dx dy is gonna be, when you do dx dr x's, that dx dr means it's gonna be cosine theta. Dx theta is gonna be negative r sine theta. Dy dr from here is gonna be sine theta, and what is that? Dy d theta from here is gonna be r cosine theta. That's gonna be dr d theta. So when you find the determinant is going to be a number, it's going to be AD minus BC, so you get r cosine squared theta plus r sine squared theta dr d theta, and that would really become dx dy is going to be r dr d theta. That's another way to look at it. So either you get dr d theta using the geometric explanation like that, or using the Jacobian like this, but we are going to use this to convert from polar coordinates to the from rectangular coordinates to the polar coordinates. And the reason why we need polar coordinates is sometimes finding volumes in rectangular coordinates becomes difficult, so we are using the polar coordinates. Now let's see an example. This is an example problem in your textbook as well, but let's go through that. Okay. Here evaluate this, where D is the region in the upper half of the plane bounded by the circles x squared plus y squared equals 1 and x squared plus y squared equals 4. So if you look at it, I mean, you know, this is going to be x squared plus y squared from the previous one. Here going to be r squared equals, okay, r squared equals 1. So that's going to be between r squared equals 1 and r squared equals 4. So applying the square root, you get r equals plus minus 1 to r equals plus minus 2, right? But remember, radius can be 0, so you are really changing radius from 1 to 2, if I understand it correctly, okay? Then the upper half of the plane bounded by the circles here. So circles means, you know, if you take like 1 1 1 1, so you get that, and you know, 1 1 1 1, so that's gonna be that. So you're in that space. So I mean, your theta is really varying from 0 to 2 pi. That's what I want you to understand. Now if you try this using rectangular coordinates, I don't know what I will get, but you can try it. I'm not going to try it. I mean, you know, I'm not going to try it, but you can try. If you're trying it, I think your x is going to vary from 1 to 2, and your y also should be varying from 1 to 2. That should not be bad at all, but that's one way to go about it. So now here, what am I gonna do? I'm gonna substitute x is gonna be r cosine theta, and you have y is gonna be r sine theta, right? So that's gonna be integral, double integral. You have 3r cosine theta plus 4r squared sine squared theta. Then you replace it with r dr d theta. And your radius is varying from 1 to 2, and your theta is varying from 0 to 2 pi. You see, first variable was dr, so that's why I'm putting the limits of integration to be radius here. The second variable is d theta, so I'm going to put the limits of integration to be from 0 to 2 pi. Okay. So that upon integrating, what do you get? I mean, you know, let's first simplify it. Okay, 1 to 2. Let's go step by step because I can't really skip steps myself. 4r cubed sine squared theta dr d theta, right? So that means that upon integrating term by term, what do you get? I mean, when you integrate, you're first integrating with respect to dr, so when you integrate it, you get 3 times r cubed divided by 3 cosine theta plus 4 times r to the 4 divided by 4 sine squared theta, where your limit of integration is from 1 to 2, and that's going to be d theta. Right, so then where are we? This is where 3 gets cancelled out, 4 gets cancelled out, so you're going to substitute for 2 now, so you get 0 to 2 pi. So you get, 2 cubed minus 1 cubed cosine theta plus you get 2 to the 4 minus 1 to the 4 sine squared theta. D theta. Let's just put it that way. Okay. So you get 0 to 2 pi, 2 cubed is 8, 8 minus 1 is 7, so you get 7 cosine theta plus 2 to the 4 is 16, 16 minus 1 is 15, so you get 15 sine squared theta d theta, right? Are you with me now? So now let's start integrating. So term wise, if you integrate 0 to 2 pi, you get 7 cosine theta d theta plus integral 0 to 2 pi 15 sine squared theta d theta, right? Are you with me now? So now 7 is a constant, so pull it out, and integral cosine theta is sine theta, where your limit of integration is 0 to 2 pi plus 15 is that, and you want to use a double angle formula to integrate it. When you use a double angle formula to integrate it, I think it was 1 minus cosine 2 theta divided by 2 d theta. Okay, if I'm wrong, fix it. Okay, so this is going to be 7 times sine 2 pi minus sine 0, okay, plus 15 over 2. Then you get integral 0 to 2 pi 1 d theta minus integral 0 to 2 pi cosine 2 theta d theta. I hope you saw that. I pulled out the 2 outside and made it 15 over 2. Okay, sine 2 pi is 0, sine 0 is 0, so the entire term goes to, and 7 times 0 is 0, so you're left with really 15 over 2 times integral of 1 d theta is going to be just a theta, where your limits of integration is from 0 to 2 pi minus then whatever you have. 0 to integral of cosine 2 theta is going to be 1/2 sine 2 theta, where your limits of integration is again from 0 to 2 pi. Okay, so now you get 15 over 2. I hope I get the right answer after all this. 2 pi minus 0 minus 1/2 times, upon substituting the limits of integration, you get sine 2 pi minus sine 0. So sine 2 pi is 0, sine 0 is 0. So you get 15 over 2 times 2 pi. That's going to be just a 15 pi. Okay, 15 pi. Am I right? I hope I'm right on this. If not, fix it. Okay, let me refer to, because this is a textbook problem, let me refer to the textbook to see if I have got a right answer or not. So what do I have? Upper half of the plate. So no, this is wrong. The reason being, we are really interested in the upper half. That means we are only interested in this region. So that means this is 0, that is pi, so it's not 2 pi. So that luckily, let's see how much changes. 0 to 2 pi, 0 to pi, 0 to pi here, and here 0 to pi here, and 0 to pi here. Okay, and when you substitute 0 to pi here, but luckily for the sine pi is also 0, so that's not changing much. So 0 to pi here, 1 minus, okay, 0 to pi here. So that's going to be 0 to pi here, okay, 0 to pi here. That's going to be 0 to pi here. So you get pi minus 0 here, okay. Then you get sine pi minus sine 0. That's going to be 0. So this is going to be just a pi. So that's going to be 15 pi over 2, okay. Yeah, I made a mistake and I fixed it. So that should be your answer. So this is how you work on it. So what we did was we discussed what we are dealing with. We are dealing with the double integrals in polar coordinates. Why? Because sometimes evaluating the integrals using the rectangular coordinates could be difficult. So that's why we are using polar coordinates. So what changes? You replace x with r cosine theta, y equals r sine theta, x squared plus y squared is r squared, and you replace dA with r dr d theta. And why do you do that? There is a geometric meaning to it, and here is the algebraic representation to that. And we saw one example where I made a mistake and then fixed it. Okay, so this is how you evaluate the volumes using the polar coordinates. I hope this makes it clear. If you have any questions, let me know. Okay, till I make a next video, you stay safe and stay healthy. Okay, bye bye.